Hello, everyone. Welcome to today's presentation. I'm excited to talk to you about data representation in computers. On this first slide, you'll see the title of our session. We'll be exploring how computers represent data internally. Over the course of this presentation, we'll cover key concepts like binary systems, data types, and how information is stored and processed. But for now, let's get started and dive into how computers handle data behind the scenes. Now, let's turn our attention to slide 2, which covers digital representation. As we've seen, understanding how data is represented digitally is fundamental to grasping how computers process information. Digital representation is all about how we encode different types of data, like numbers, text, images, and sounds, into a form that computers can understand and manipulate. This slide also introduces the idea of numbering systems, which are essential because they provide the foundation for how data is structured and stored in digital form. Recognizing these systems helps us understand the underlying mechanics of data processing, which is crucial for effective digital communication and computation. Throughout this presentation, we'll see how these concepts interconnect and enable the incredible versatility of modern digital technology. Let's start by looking at the binary representation of data. At its core, a bit is the most fundamental unit of information in computing. It's really simple, just a binary digit, which can be either a 0 or a 1. These two values are the building blocks for all digital data. Think of them as the basic yes or no, on or off states that computers use to perform operations. Now, when we combine multiple bits, we get a byte. A byte is a standard unit of digital information. Most commonly, it consists of 8 bits. These 8 bits work together to represent a wide range of data, like a single character in text or a small piece of information in a larger dataset. Understanding these basic units, bits and bytes, is crucial because they form the foundation of how data is stored, processed, and communicated in digital systems. It ties directly into the overall theme of how information is represented and manipulated in computing. Let's talk about digital representation. Within a computer, all the information we work with is stored and represented in a digital binary format. Now, a key term here is bit, which is short for binary digit. Think of a bit as the smallest piece of data a computer can handle. Humans tend to interpret complex words and images easily, but computers don't process that information the same way. Instead, computers interpret patterns of bits, just sequences of zeros and ones. These bits are the building blocks of digital data. It's important to understand that a single bit can only have 2 possible values, a 1, which we write as 1, or a 0, written as 0. This binary system is perfect for representing 2 distinct states. For example, if you think about a light switch, it can be either on or off. In binary terms, on corresponds to 1 and off corresponds to 0. By understanding how bits work, we see how simple binary states can be combined to represent all kinds of complex information in digital systems. It's the foundation of digital representation, and it connects directly to how computers process and store data efficiently. Let's take a closer look at numbering systems. First, there's the binary system, which uses just 2 symbols, 0 and 1. Because it's base 2, the counting is quite straightforward. After 1, you roll over to 10, which is like 2 in decimal. Next, we have the decimal system, which is what we use every day. It's base 10, meaning it uses 10 symbols, 0 through 9. When we reach 9, we move to 10, which is like 10 in decimal. Interestingly, in hexadecimal, we use 16 symbols, 0 through 9, and then A through F, where A represents 10, B is 11, and so on up to F, which is 15. We also have octal, which is base 8, using symbols 0 to 7. Now you might wonder, why do these different bases exist? Well, it all comes down to what happens when we reach the maximum number a system allows before rolling over. For example, in decimal, when we count up to 9, the next number is 10. In binary, after 1, the next is 10. In octal, after 7, it's 10. And in hexadecimal, after F, it's 10 again. Each system has its own base or radix, and understanding how they work helps us see how numbers are represented in different computing contexts. Now, let's move on to the next important concept, using positional notation. This is a fundamental idea in how we represent numbers, especially in different number systems. Essentially, positional notation means that the value of a digit depends on its position within the number. For example, in the decimal system, the same digit can have different values depending on whether it's in the units place, the tens place, or the hundreds place. This system makes it very efficient to write and understand large numbers. It also forms the basis for how computers process data, since computers rely on positional systems like binary. So, understanding how positional notation works helps us grasp both basic arithmetic and the way digital systems operate behind the scenes. This concept really ties together the entire theme of number representation and processing. Let's go through the steps to convert a binary number to a decimal. First, write down the binary number you want to convert. In this case, we'll use 10,011,011. Next, list the powers of 2 starting from the right. We begin at 2 to the 0 power, which is 1, then 2 to the first power, which is 2, then 2 squared, which is 4, and so on, increasing the exponent by 1 each time. Since our binary number has 8 digits, we need 8 corresponding powers of 2. So from right to left, those are 1, 2, 4, 8, 16, 32, 64, and 128. Now, write the binary digits below their corresponding powers of 2. It's important that the first digit aligns with 128, the second with 64, and so on, matching each digit with the correct power. Once you've lined everything up, connect each binary digit to its corresponding power of 2 with lines. Start from the rightmost digit and draw a line to the 1, then from the next digit to 2, and continue this pattern. This visual connection helps us see how each binary digit contributes to the overall value. Now look at each digit. If it's a 1, write the value of the corresponding power of 2 below the line. If it's a 0, just write 0. For our example, the binary number 10,011,011 has ones in certain positions. 128, 16, 8, 2, and 1, and zeros in others like 64, 32, and 4. The next step is to add up all the values where the binary digit is 1. So, for this example, that's 128 plus 16 plus 8 plus 2 plus 1, which totals 155. This sum is the decimal equivalent of our binary number. Finally, write this number with its base subscript, like 15,510, to indicate it's a decimal number. And don't forget, writing it as 15,510 makes it clear we're working in base 10. The more you practice these steps, the more familiar you'll become with powers of 2, and converting will become quicker and more intuitive. Now, let's talk about using doubling as a powerful technique. Doubling involves taking a key concept or element and repeating it to reinforce its importance. This can help make your message more memorable and impactful. For example, when you emphasize a point twice, it signals to your audience that this is a critical idea they should pay attention to. Doubling can also be used to create rhythm and emphasis in your speech, making your presentation more engaging. It ties into the overall theme of making your communication clear and persuasive. By strategically doubling key points, you ensure that your audience not only hears your message, but also retains it. So remember, doubling isn't just about repetition. It's about reinforcing your main ideas in a way that sticks with your audience and enhances your overall message. Let's walk through the steps for the doubling method. First, write down the binary number you're converting. Remember, this method doesn't involve powers, so it's simpler for mental math, especially with large numbers, because you only need to keep track of a subtotal. For example, suppose our number is 10,110,011. Write it down clearly. Next, start from the leftmost digit. The process is to double your previous total and then add the current digit. Since we're starting fresh, our previous total is 0. The first digit on the left is 1. Double 0, which stays 0, and then add 1. That gives us 1. Now look at the next digit, which is 0. Double our current total of 1, which gives 2, and then add 0. So 2 plus 0 equals 2. Our new total is 2. Repeat this process. Double the current total, then add the next digit. The next digit is 1. Double 2 to get 4, then add 1, which totals 5. Our current total is now 5. Again, double the current total, which is 5, giving us 10, then add the next digit 1. That results in 11. So our total becomes 11. Next, double 11 to get 22, then add the next digit, 0. So, 22 plus 0 remains 22. Continue the process. Double 22 to get 44, then add the next digit, 0, for a total of 44. Keep going, double 44 to get 88, then add the last digit, 1. That's 88 plus 1, which equals 89. And that's it. The binary number 10,110,011 converts to the decimal number 89. Remember to write your answer with its base subscript, so it's 89 with a small 10 to show it's in decimal form. You can use this same doubling method to convert numbers from any base to decimal. Just replace the 2 with the base of your number. For example, if your number is in base 37, you would multiply by 37 instead of 2 at each step. The final answer always ends up in decimal, base 10. This method is powerful because it simplifies the conversion process, especially for large numbers, by focusing on doubling and adding digits sequentially, keeping calculations straightforward and manageable. Now, let's practice converting some binary numbers into decimal. Here we have 3 examples: 11,010,011, 11,001, and 11,110,011. The key idea here is understanding how binary numbers translate into decimal, which is more familiar to us. For each of these binary numbers, their decimal equivalents are 209, 25, and 241, respectively. Recognizing these conversions is essential because it helps us interpret binary data in a way that's meaningful and easier to work with, especially when dealing with real-world applications. Remember, mastering these conversions ties directly into our overall theme of understanding how computers process information at the most fundamental level. So, keep practicing these conversions, and you'll see your confidence grow in handling binary data effectively. Let's walk through how to convert a decimal number, like 25, into its binary form. First, we divide 25 by 2, which gives us a quotient of 12 and a remainder of 1. Then, we take the quotient 12 and divide it by 2 again, resulting in a quotient of 6 and a remainder of 0. Continuing this process, 6 divided by 2 gives us 3 with a remainder of 0, and 3 divided by 2 gives us 1 with a remainder of 1. Next, dividing 1 by 2 yields a quotient of 0 and a remainder of 1. The key here is to note that the remainders, read from bottom to top, form the binary number. So, starting from the last remainder we got, which is 1, then 1, 0, 0, and finally 1, we get the binary number 11,001. This method is a systematic way to convert any decimal number into binary, and it ties into the bigger picture of understanding how computers process data, since binary is the fundamental language of digital systems. Remember, the most important part is to perform repeated division by 2, keep track of the remainders, and then read those remainders in reverse order to find the binary equivalent. Now let's walk through how to convert a decimal number into its binary equivalent. Here, we're checking the number 25. On the left, we have the binary multiplier, which is 11001. This represents the binary digits we're testing. On the right, we see the decimal equivalents, 16, 8, 4, 2, and 1. These are the values of each binary digit position. To verify the conversion, we multiply each binary digit by its corresponding decimal value. For example, the first digit is 1, so 1 times 16 gives us 16. The next digit is also 1, so 1 times 8 equals 8. The following digits are 0, so their contributions are 0. The last digit is 1, which is 1 times 1, giving us 1. Adding these results together, 16 plus 8 plus 0 plus 0 plus 1, gives us a total of 25. This confirms that the binary number 11,001 corresponds to the decimal number 25. Understanding this process is fundamental because converting between decimal and binary is essential in digital systems and computer architecture. All right, now let's put our knowledge into practice by converting these decimal numbers into binary. We'll start with 1. When we convert 1 to binary, it's simply 1. Next, 19 becomes 10,011 in binary. For 2, it's quite straightforward, just 10. Moving on to 28, which converts to 11,100. And finally, 37 translates into 100,101. As you perform these conversions, it's essential to verify your answers. Double-check by converting back to decimal to ensure accuracy. This step helps reinforce your understanding of binary numbers and their relationship to decimal values. Remember, mastering these conversions is fundamental because binary is the language computers understand best. It connects directly to how data is stored, processed, and transmitted in digital systems. So, take your time, check your work, and see how these numbers translate seamlessly between decimal and binary. Thank you for your attention, and I hope this exercise solidifies your grasp of binary conversions as part of our overall journey into digital systems.